Welcome to this new video, guys. Hope you guys have already watched my last video where I covered mostly the vector basics as well as some kind of vector operation we have covered. Now we'll try to continue from that particular video, like what we have left. We have left from cross product of vector operation, right? The next operation of vector is called, we'll be calling it as what? We'll be calling it as L2 normalization and L1 normalization. So I'm saying L1 normalization. So when it comes to L1 normalization, we also mostly call it as we call it as Manhattan distance. Okay, Manhattan distance. I hope you guys already heard about these kind of terms: Manhattan, Euclidean. Those are some scientist names, right? Some mathematicians name, and we will be figuring out what it actually means. So when it comes to Manhattan distance, what L1 norm does is, it's nothing but it is mostly the sum of absolute value of absolute values of your elements, hopefully you guys already know what is a vector means, right? When it comes to a vector, we mostly represent a vector in a Python term. We will be representing a vector in a list, right, which is called a series. Hope you guys already remember that. So let's say I'm having a series like this, which is called a list. In a mathematical term called a vector. For me, x is equals to 3 minus 4 2. The elements is having 3, which is a three-dimensional vector right now. So when it comes to L1 normalization, your vector will have absolute value of each element. So what did that mean? That would be x1 absolute value, x2 absolute value, and x3 absolute value. So what we are trying to do here is, if I'm just boxing it out, so that you will be understanding what I'm trying to do here, the formula as well. So now for our case it will be like 4, sorry, it was 3 minus 4 2. So let's say 3 magnitude of 3, magnitude of 4, and magnitude of 2. So if we'll be calculating out, it will be 9, right? The value of x, the Manhattan distance of x vector is actually 9. What is the intuition behind it? So if you'll be thinking, what is the intuition behind it? Think like you are moving through a city. Okay, I'm giving you an example here now. Think like you are moving through a city. Okay, you are moving in a city or through a city. The proper word will be through a city, right? You are moving through a city, and where you can only travel, you can only travel you can only travel okay, you can only travel horizontally or vertically. Okay, when I'm saying that, or and and vertically, or will be wrong. Okay, so it will be and vertical roads. So what you will be doing, think about, you will have a vector, sorry, I'm very much bad at my drawing. Okay, so you'll have a vector, like say I'm currently in a two-dimension space. In my two-dimension space, I'm having two vector. Let's say obviously I got you into some kind of example where x is there, only one vector. You can have two vector as well. So think about, I'm having two vector now. Okay, in this two vector, I'm saying this is my x, and this is sorry, let's x axis will be, the naming will be conventional, will be little bit odd, right? So let's do a and b. The moment I'm saying this like this, and I said in L1 normalization I can only move vertically and horizontally, horizontal and vertically. So what we can do here, the movement of this thing can happen only through like this. See this, 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 this way, this way. So 5, this is 6. Okay, so if you'll be seeing closely, how many steps I have taken? 6. Okay, 1 2 3 4 5 6. If you are taking 6 steps to reach from a point to b point, which is a vector to b vector, it is called Manhattan distance of Manhattan distance of Manhattan distance is equals to 6. If your Manhattan distance is 6, what will be your Euclidean distance? If your Euclidean distance, the Euclidean distance will be this one, which we'll be discussing about later. So now if I'm saying Manhattan distance, it is nothing but my L1 distance. So if you'll be looking closely, this step I have taken 6 steps. What would have happened if the same distance I can cover something like this? I can cover something like this. This is a horizontal step. This is a horizontal step road, and this is a vertical step road. So in this case, your L1 will be 2. Yes or no? So your Manhattan distance, your Manhattan distance, you should not be always have one way to go it, right? From A point to B point, because I am telling you now, you are moving through a city from A point to B point, and you can only go for horizontal and vertical roads. You can go through lot of options can be possible, right? There are 2, there are 3, there are 6, and you will be choosing the optimal one, correct? So this is something which called L1 normalization. So what will be the L2 normalization, right? This is starting is point is, I think we are covering fifth operation of vector. We are going to cover the sixth operation of vector, which is called L2 L2 norms. Okay, not normalization. Normalization you can say it, but L2 norm sounds good, right? And also it is called Euclidean distance or Euclidean length. Okay, when it comes to Euclidean length, think carefully. This L2 norm, this L2 norm, L2 norm, L2 norm is the usual straight line, okay, straight line length vector. So we already know what is a straight line does, and a straight line length vector. So if you will be remembering closely in our 12th class physics, you might have studied these kind of concepts, right? But I'm here to explain you again. So what is the formula here? So think about every particular point of yours is moving from one point to another point. So now your vector x will have the absolute value of 2, which is L2 norm, which equals to x1 square, x2 square up to xn square root over square root of x1 square, x2 square, x3 square up to xn square root. Any doubt? Guys, any point of you are having any doubt, just comment down below, okay? Now if I'm saying for the same vector which we took before, our x used to be 4 minus 3 2, right? Remember? No, sorry, what was that? 3 minus 4 2, 3 minus 4 2. Let's do L2 norm on this same vector, right? If you'll be doing L2 norm in the same vector, I'll be having what? I'll be having 3 square plus minus 4 square plus 2 square root of this, right? Now if you'll be seeing, it will be having 9 plus 16 25 plus 4, which is 29. Square root of 29, you will be getting nearly 5 into 5 5 into 5 into 25, not like that, it will be 25 plus 4, right? So it will be nearly equal to 5 point something. You will just figure it out, okay, in your calculator. So intuitively, if you be thinking intuitively, imagine I'm drawing a straight line, okay, I'm drawing a straight line from here to here, and the point here is, I'm talking here, the point should be origin. When I'm talking the point will be origin, tell me one thing. Tell me one thing. The point here is origin and the point here is my original point. If you are seeing something like this, do you think this diagram is exactly correct? Because the diagram is wrong. Why? We should have three-dimensional vector, right? Currently we have two-dimensional vector, right? So this, oh sorry, because we have 3 points now, x and y and z, right? So let's say this, right? If you will x, y, z, 0, 0, 0, and your point is 3, 4, minus 4, 2, and you are finding the distance, okay? You're finding the distance here, which is t, and I'm saying that d is nothing but my Euclidean distance. And if you'll figure it out, the formula is coming like this, right? It's nothing but d is equals to 3 minus 0 square plus minus 4 minus 0 square plus 2 minus 0 square root of this. So now you will be finding some values of d, right? You will be finding that some values of d, which is 5 point something. What is one point you are missing here? So if you're seeing same concept what I draw here with the same example, it will be coming here. Isn't it look like d? So here that is what d is equals to your Euclidean distance. We figure out in the below, okay? Below here I completed out, right? That is what the difference between L1 norm, L2 norm, and I will be telling you one thing, right? When it comes to data, you will have data, right? In data we will mostly have outliers, okay? So you will be saying out of two, when it comes to L1 norm and L2 norm, which one do you think is having some kind of sensitivity towards, which is called outlier? The L1 norm is very much sensitive to outlier. Hopefully you guys know what is outlier means. Outlier means, think about a data point where you will have data points like, let's say you are selling a mango, you are a mango seller. In your as a mango seller, as a mango seller, you are selling prices around 10, 20, 15, 5. Okay, you are selling a mango in this range. The moment your mango price selling range becomes like this, okay, don't you think this one seems like an outlier to this whole process? Because this is never going to happen always, the price difference. The moment you will having a average of your per day average of your mango salary, mango selling price will be around what, 10, 20, 30, 30, 40, 45, 50. So it will be 50 by 5, oh sorry 4, around 12 point something, right? But if you, the moment you will be adding one more here, it will be having 150 by 5, which is having value of what, 30. There is a huge difference between this average and that average, right? This average and this average. So that's why we will be covering up the outlier part. We will be covering up in the later classes, like when we will be covering the statistical part. But currently, hopefully you know what is sensitive outliers to mean, and this is the L1 are mostly less sensitive, I want to say, okay, and this is more sensitive. Sensitive means it will be having some issue, okay, that's what it sensitive means, right? Sensitive to outliers. So hopefully you guys are clear about what is L1 norm, what is L2 norm, right? Yes, these are all vector operation. We are still any point of doubt you are having, any point of doubt, you just let me know. Great. So do you think which one of them would be better for what kind of model? Like, let's say I can say ki we have L1, we have L2, I'm highlighting it little bit more because this is going to be very much useful in your real world examples, right? So let's say if you are having some models, in that model you are having some kind of weight, like errors. So the moment you will be getting errors, the moment you will be getting overfitting issue, you will be getting these kind of issues, we mostly try to figure it out through something called regularization. And those regularization you will be adding some kind of penalty to it. So what happen if your model is having some kind of overfitting issue? Overfitting issue means it is memorizing things. Okay, it is memorizing things means you will try to add some penalty to it penalty to it to just to tell him ki, like, because you remember something, that's why I'm adding some penalty to it, so that your accuracy, you will be like kind of forgetting something, and or you will be trying to learn the pattern rather than memorizing it. So we are kind of adding the penalty to it, and the penalty is nothing but, if you'll be thinking logically, it's kind of reducing the particular accuracy, right? If your accuracy is pretty high, that's where overfitting issue comes in, and that's where the penalty will be working fine. And think now, if you are adding a penalty, let's say I'm adding a penalty of L2. Okay, L2 mostly used in reach, which is called reach regression. Again, I'm telling these things will be coming up later on. Okay, what there I'm trying to used L2 in a squared value. I'm penalizing it in squared value, right? The other one I'm trying to penalizing it the L1, which is called the N1 penalty, which is called lasso regression. Okay, lasso regression, when trying to penalizing using absolute value. The thing is it is pretty easier to understand. Slowly we'll try to connect these things with your uh, law, like machine learning concept and mathematical concept. It's really needed, that's why I'm telling you. So in easiest way I can say, when you will have L1, you try to add absolute value. Okay, add absolute value, and the more you will experience, you will be getting some sparse model. Hopefully you understood the English meaning of sparse. I don't want to explain that, right? And when it comes to L2, which is nothing but square value, we are adding square value, and that model will be having something called smaller words. This is the easiest way to understand why we are learning these concepts and how it is going to be used. Okay, only one more concept remaining in vector operations, which is called you know which is called unit vector. Unit vector, I hope you guys know what is a unit vector. If you don't know, again, I'm here to explain you, right? So what is unit vector? Unit vector is nothing but its magnitude is going to be exactly 1. So its magnitude is going to be exactly 1. Exactly 1. What does that mean? What is magnitude mean? If you don't know, just hit your head to the wall once. So now what is that means? If you have u vector, okay, of some elements, I don't want to write it now. So what is the magnitude of it? The magnitude of it is nothing but double bar, right? This one is 1. This is what we are asking, guys. This is what we are asking. And we already discussed about the u double bar, right? Double bar, this surrounded by double bar, already known, right? If you don't, let's cover it up, don't worry. So what actually mean, if you will have a u vector of element like 3 and 4, two element, what we do in this is nothing but 3 square plus 4 square root is nothing but 25 root is 5, right? So now tell me one thing, This isn't it looks like L2 norm? This is looks like L2 norm, right? The moment you find out the L2 norm, let's try to convert it into a unit vector. How? To convert into a unit vector, what you need to do, you need to divide your vector by the this particular magnitude vector, right? So magnitude normalization of value. So what we are trying to do here, I'm saying u is nothing but u by this L2 norm. Okay, I can write it like this now, L2 norm. Just remember the symbol understanding is pretty important. So what we are trying to do here, is u is equals to 1 by 5, 3 and 4 is nothing but 3 by 5, 4 by 5. What is these values is going to be? The values is going to be 0 0.6, 0 0.8. No doubt, if you find out 0 0.6 and 0 0.8, now what this is nothing but it's you never going to tell it as a u, right? You are going to tell it as a new value, and that new value is v. See, we started with u, the value was 3 and 4. Now if you will be saying again it is same vector, it is not the same vector, right? So I can change the symbol here. So let's say b. Okay, you will not get confused, otherwise at the end you will be saying how it is coming from u to v. Okay, don't worry. So now v is equals to this, we did this particular thing. This is the formula. Now the moment you got some values of b, what do you need to find? Let's verify it. How will we be verifying it? We'll be verifying with the same concept, the normalization concept. Now you will try to find out the L2 normalization of new vector v, and we are trying to figure it out using square of it. You will be finding 0 0.36 plus 0 0.64. You will be finding square root of that is nothing but 1 square root is, oh my god, what does that mean? That mean, so v is a vector. Okay, again I'm writing vector. V is a vector of value 0 0.6 and 0 0.8 is a unit vector. Let's look into it. We started with a value which is nothing but with a vector called this. When trying to convert this vector into a new unit vector, right? I'm writing again. I'm trying to convert it. We're trying to convert it. We're not checking it. We're trying to convert it into a unit vector. Okay? To convert it into a unit vector, we applied this formula, and then we try to figure it out whether it is a unit vector or not. Guys, any doubt about this concept? Any doubt? If you don't have any doubt, if you have a doubt, if you don't have, it is an issue, no issue. If you have a doubt, just drop a message in the comment box. I'll be always here to help you out. Clear? Great. See you in the next video with matrix operation. Bye bye.